All right. So here's a problem out of your book. I don't know if this is from your book or from a previous edition, but it was problem 237 in the book. It wants to know the horizontal and vertical reactions at A and C. And it calls it a two-member frame. Let's talk about a strategy. If I can draw a free body diagram of the whole structure, if I do that, how many reactions would I model here at A? It's a pin. 2. So there's 2 unknowns at A. How about over here at C? Also 2. So I could get some information from a free body diagram of the whole structure, but I wouldn't be able to get it all because I have 4 unknowns and only 3 equations. Now the savior for this particular problem is if you look at the structure carefully, you'll notice at B, what is that? It's a pin. And similar to our previous problem, we know that at a pin, what's true about moment? It's 0. So I don't have to solve for it there. So if I take this structure apart into a free body diagram of AB and a second free body diagram of BC, then I will generate how many new unknowns here at a pin? 2. So now I'd have 2 at A, 2 at B, 2 at C, 6 total unknowns. And how many equations do I generate? Well, I'll get 3 from my free body diagram AB and 3 more from BC. 6 equations, 6 unknowns. You can do it that way if you like. But there's kind of a shorter, more efficient way. So let's first examine AB. Is AB a 2-force member? No, it's because it has some loads applied, right? What about BC? Is that a 2-force member? Yes, it is. So that means I don't have to say BX, BY. I know exactly the direction of that reaction. It's going to be the line connecting B and C. I know the direction. I just don't know the magnitude. 1 unknown. So now when I take this part AB apart, I'll have 2 unknowns at A and only 1 unknown at B. Almost very similar to the problem we just looked at. All right? So let's do that. So I'm going to draw let me do it over here. Let me think about this. I'm going to do this. Yeah, I'll do it here. So let's do a free body diagram of section AB. So there is the structure. It's 5 meters tall. At A, I'm going to assume I have a reaction in the Y, a reaction in the X direction. At B, right, we just talked about BC being a 2-force member, so the line of action between B and C will tell me the direction of that force. And I'll just call it the force at B. And what is this thing going to be? Well, notice that if you did connect this line across here, that has a run of 4 to a rise of 5. Right? So that's a weird triangle. We'll have to come back and figure that out. That's not a nice 3, 4, 5. It's a 4, 5. I don't know what it's going to be.
6.4.
What is it?
6.4.
Square that. Square root of 49?
No, I thought it was 6.
Yeah, what is it? Let's square it. Give me a square root. 21?
41.
41. Thank you. So I'm going to write it that way. It'd be easy for me to write square root of 41. So this is going to be I like to draw it on there so I remember it's a 4, 5, and then of course the hypotenuse is square root of 41. We'll come back for that in a second. What about my force here on the left, the distributed force? Again, we'll do a concentrated equivalent. It's a rectangle, so it'll be the base times the height. The base is the height of the structure, which is 5. What's 5 times that? 350. 1750? So that's 1750. That's newtons. and it happens through the centroid. The centroid, that is half the distance, so this will be 2.5 meters up, 2.5 meters. I'm thinking that I might need some components here, so I'll go ahead and draw those just so I can see their direction. What would the horizontal component be here? What's going to be the ratio of 4 to the square root of 41, right? So you'll get something that looks like this. 4 to the square root of 41 FB. Now you don't have to do it this way. I do it this way because up here I don't need a calculator so much. I don't have to convert things to angles. I don't have to then take sines and cosines. Remember this angle, if you want the cosine part, it's just the adjacent over the hypotenuse. So that's the adjacent over the hypotenuse. That's just the cosine of the angle. A lot of times if it's a 3, 4, 5 triangle, it's really easy. It's 3 over 5, it's 4 over 5, and then the calculations are simplified. And I will alert you, your author really likes the 3, 4, 5 triangle. So keep an eye out for it. He hides it in he'll multiply by 3 or 4 or 5, and it doesn't look like explicitly a 3 to 4, but it is 3 to 4. So keep an eye out for that. Okay, I think that's all we need there. Can we solve this system? Well, sure we can. Where should we sum moments? Can you sum at B? Sure. You should be able to find what? AX. What if you sum at A? You can find B. So it's up to you. I'm going to stick with my strategy that we applied previously. I'm going to sum moments at the pin, which in this case is A. I'm going to set it equal to 0. So there's my equilibrium statement. So let's do it. Summing moments at A. Obviously, AX, AY don't create moment. What about this force here? The horizontal force. It creates what kind of moment? Positive or negative? Positive. So it's going to be 4 over the square root of 41 FB. That's the horizontal component. And the moment arm is the height of the structure, which is 5 meters. The vertical component passes right through A, creates no moment. And then I'm left with what? Just my force. What kind of moment does this force create about A? Positive or negative? Negative. And the force is 1750 newtons. And the moment arm is, we've already indicated here, it's 2.5 meters. So I should be able to solve for the force in B. It looks like it's going to be positive. I don't know what that number is. You guys will have to calculate that for me. I think it's going to be 3,500. I have no idea. I'm just guessing. No, 3,500. Less than 3,500. Yeah, what'd you get? 1680. 1680? That could be. I don't know. You tell me. Oh, it should be half. Yeah, I messed up. I went the wrong way. I'm trying to do my Rain Man calculations. It's not working for me. Only one person got a number? 1,400? Exactly?
14.8. Yeah.
Close enough. So 1,400 basically, right? And that would be newtons. That's close enough. For me, 3 significant figures is good enough for most calculations. All right, cool. So now what do we do? Some forces in X, some forces in the Y. I don't see a real big advantage. Maybe summing forces in the Y would be a little easier, so we'll do that one first. So I'll assume it's up. We'll sum forces in the Y, make sure it's equal to 0. So there's our statement. So what is in the y direction? I've got AY. It is acting up, so we'll assume that's positive. What else is acting in the y direction? Looks like the y component of FB, right? And that's also up. And that's going to be 5 over the square root of 41 FB. And of course we know FB, so plug it right in there. It looks like AY is going to be negative. 1091? 1094. Anybody else get 1094?
Yes.
Yep. And that's also newtons. Does it make sense that AY is negative? I assumed it was up, so it's really down. Why do I have to hold the structure down at A? Well, look at this big horizontal force. How is this structure going to try to rotate? If you were looking at C as a rotation point, how would this structure rotate? Clockwise or counterclockwise? Clockwise. No, counterclockwise, right? Oh, clockwise. I'm sorry, clockwise. So you'd have to hold it down to keep it from rotating. That makes sense. All right, let's finish this off. Let's sum forces in the x direction. Make sure we're in equilibrium. I'm going to assume right is positive, so I've got AX to the right. And I've got my concentrated equivalent to the right, 1750. And what else is in the horizontal direction? My x component at B. And it's to the left, so that's negative. And that would be 4 over the square root of 41 FB. And again, plug FB in there. You should be able to solve for AX. I think it's going to be negative, isn't it? Maybe not. Yeah, I think it is negative. What'd you get? 875. Anybody else?
Yes.
Yep.
Okay. All right. Cool. Are we done? Technically, no. What we could, since I explicitly asked for the reactions at C, now I'm going to come back and draw a free body diagram for C, which is just a point. And remember, equal and opposite. So there's my force in the B direction. Remember, it has the same slope, 4 to 5. And then I'm going to assume that I have a CY and a CX reaction. So since I explicitly asked for it, we're going to have to go ahead and finish this up. I'm going to sum moments at C. Will that help? I always say sum moments at the pen, right? Why would that give us nothing? All the forces are concurrent at C, so there are no moments. So that won't help. So we'll have to do something else. So let's start with summing forces in the y direction. So there's my static statement. So let's look at forces in the y direction. In this case, CY is up, so I say that's positive. And then I've got my reactions for the force at B. What's the vertical one? It's acting down, and that's really 5 over the square root of 41 FB. Right? So that's going to be negative 5 over the square root of 41 FB. So once again, we have to put FB in there. So what does that tell me CY is? Looks like CY is going to be positive. Say again, 1091? 1094. And then we'll finish off by summing forces in the x direction. Make sure that's an equilibrium. So there's our equilibrium statement. So what do we have in the x direction? I've got Cx to the right. That's positive. And then I've got this horizontal component of FB. So that's going to be 4 over the square root of 41 FB. That's that part. And that's to the right, so that's also positive. So that looks like Cx is going to be negative. What's that?
875.
875.
Negative,
Cool. So looking back at the whole structure, put back together, AX and CX need to balance the X force. And if you look at the two AX and CX, you add them together, what do you get? 1750. And since the applied force is acting to the right, you'll notice that both of those are going to the left. So that balances that. What about vertical? Well, there are no vertical forces applied, so if you sum AY plus CY, you should get 0. AY is negative 1094. CY is positive 1094. They cancel. So it seems like we're okay. Any questions about that one? You will know there's one critical point here. If you miscalculate FB at the beginning, you're toast. Right? Now, here's the savings grace for you. If you're doing this for homework and you miscalculate FB, well, you don't get anything right. Right? It does let you try a few times. Maybe you eventually get it right. On the exam, if you screw up here, if your free body diagrams are correct and your equations are correct, it is somehow in computing all this, you end up with, I don't know, make up some number, 1275. Oops. Right? I'm going to follow that through, and if your equations are all right, you'll still pass the problem, even though you got none of the answers right. That's rare in engineering, that I reward you with a successful thumbs up when you got all the answers wrong. Because, for me, right now, it's more important that the strategy and the logic you apply. I want you to get the right answer, right? But I'm not going to crush you if you don't get it. You're not going to get a 0. So make sure you do focus and that you communicate to me clearly your logic. Don't be one of those people who shortcuts everything and just writes out an answer. Because if you do that, I may not give you any points. Yes?
What about if you look at the body as a whole and then there are 2 unknowns at A, 2 unknowns at state part, if you take one at like AS and CX, right, same direction, and then
if you drew a free body diagram for the whole structure and you summed in A, you would find CY.
Yeah, is it okay to do that?
And then you could well, here's the problem. Then you sum forces in the Y direction, you get AY. What happens when you sum forces in the X direction? What do you get? AX is equal and opposite CX. That's all it gives you. It doesn't give you the value. You could do that. But you're still going to have to take it apart somewhere and eventually find one of the X components to be able to find it. I just thought it'd be more instructive now just to go ahead and take it apart, do one whole piece, and then do a second piece. But you could. And sometimes that's an advantage. Get as much information as you can from the whole structure before you start taking it apart. You can do that also. All right. How much time is left in class? Not much. I think what I'll do is not work any more problems. I think I'll go ahead and start talking to you about Chapter 3. So as far as I'm concerned, we're done with Chapter 2 because I thought Chapter 2 was kind of almost kind of a review and kind of get you thinking about structures and get your status back going.